Dear students, welcome to the EPG Pathshala. I am Dr. Gurmeet Singh, working as a professor in the chemistry department of University of Delhi. Today we are going to discuss about the module called Electron Spectroscopy for Chemical Analysis, or it is abbreviated as ESCA, ESCA. We have already dealt with the introduction and about the instrumentation. In this module, we shall talk about data analysis, uh, how this is carried out, what is the importance of this. All these factors we shall elaborate in this particular module. And this module comes under the paper of Surface Analytical Techniques, Part 1. After completing this module in a pretty fairly detailed manner, you will always be able to understand and explain subsequently that what ESCA studies of polyamide or pyrometallic dinhydride or oxydianylide, abbreviated as PMDA or ODA, etc., can be done with the help of this. So the ESCA studies of some of these compounds can be conveniently done while they are on the surface. Chemical states and chemical shifts can be very precisely measured with the help of this equipment. Coming to the data analysis, we find that the ability to produce chemical state information as distinguished from merely elemental information from the topmost few nanometers of any surface makes XPS a unique and valuable tool for understanding the chemistry of any surface. As I have said, this is basically a surface analytical technique, and very precisely one can find out what exactly is there on the surface and to what extent it is there. That means it provides us both qualitative as well as quantitative data when we go down to the analysis of any species. The local bonding environment of a species in question is affected by number of factors. The first one being its formal oxidation state. The identity of its nearest neighbor atom can be measured when we look at the oxidation states of a particular metal in a material. Its bonding hybridization to that nearest neighbor atom. This also has been done, and we have got some very interesting results in our experimental research work. The bonding hybridization between the atoms in question and the next nearest neighboring atom can also be found out and checked experimentally. Chemical state analysis is very widely used for the chemical elemental carbon. Chemical state analysis of the surface of carbon containing polymers rarely reveals the presence or absence of the chemical state of carbon shown in the letters in bold form. Chemical state analysis of the surface of a silicon wafer rarely reveals chemical shift due to the presence or absence of the chemical states of silicon in its different form of oxidation states. These states could be N-doped silicon or P-doped silicon, that is metallic silicon in the figure given above, or silicon suboxide Si2O, or silicon monoxide SiO, or silicon dioxide Si2O3, or silicon dioxide SiO2, or the other silicon higher order oxide Si2O3. Continuing on data analysis, the graph or the spectra of an organic compound called polyamide pyrometallic dinhydride oxydianiline. In short, it is called PMDA-ODA. This has been shown in this slide, and the structure of this compound has also been given, which is made out of two parts. One is dealing with PMDA and the second deals with ODA part, and they have been linked and you get this complex molecule. This, when it is subjected to ESCA studies, we get a spectra of the kind which has been shown, wherein binding energy and XPS intensity are recorded, and we find that it indicates the presence of oxygen in two forms and carbon and nitrogen in the surface, from which we can even get the extent of these on the surface and will prove the presence of this. Structure of the two units, PMDA and ODA. These have been given, and the possibility of the nitrogen and oxygen in different structures have been put here. The data on about this compound, here what way a particular element reacts with another one and what are the changes in the peaks have been given here. The first talks about the binding energy and the XPS intensity pertaining to PMDA and ODA. You have the carbon, then oxygen in two forms, and those two peaks have been indicated there. So this way, how the spectra of this compound will look like has been presented in this slide, and we have O1s spectra given, and then the way the release of water upon curing takes place is also given. And information about XPS analysis of pigment from mummy artwork. Mummies were very ancient structures or statues which are found in Egypt, and these are very old World Heritage structures. The Egyptian mummy, which belongs to 2nd century AD, as was taken from World Heritage Museum from the University of Illinois, that photograph has been shown in this slide. And on the right side of this, the way the spectra looks like has been given. XPS analysis showed that the pigment used on the mummy wrapping was of lead 304 rather than Fe2O3. The normal understanding was that these mummies have a paint of iron oxide on the surface, whereas when the analysis was carried out, it was found to be having Pb3O4. This is proved by the spectra there because it shows lead there in two forms, and those lead peaks have also been shown as PbO2 and Pb3O4, and two lead peaks also have been indicated in the other spectra of this pigment. So this is one of the good applications of ESCA when we talk about the analysis of pigments or paints on the surface of various artifacts are concerned. Here the example of an Egyptian mummy has been taken, and it has been shown that the paint at the surface, the pigment used at the surface, contains lead and not iron. Analysis of carbon fiber. Carbon fiber is a polymer composite, and this material has been analyzed by XPS. Woven carbon fiber composite has been shown, and that has been used by some racing drivers for their clothes. XPS analysis identifies the functional group present on composite surface. Chemical nature of fiber-polymer interface will influence its properties. This slide indicates the analysis of materials for solar energy collection by XPS depth profiling. This slide shows that the material contains amorphous silicon carbide and tin dioxide. This interface it has. The profile indicates a reduction of SnO2 tin dioxide. This reduction occurred at the interface during deposition. Such a reduction would affect the collector's efficiency because it should have more of SnO2, thereby it will be able to collect the higher amount of energy. But this reduces and the capability of this collection also reduces. It has photovoltaic collector which is made up of this SiC and SnO2. So solar energy falls on the conductive oxide layer which is SnO2. In between we have a p-type SiC and then we have anodic silicon. So when it falls, SnO2 should be there. If tin dioxide layer reduces, it will reduce the ability of this material to store solar energy. This extent will reduce, and one notices that this, once it goes down, this can be proved or shown with the help of ESCA spectra, whereby the tin peak would get reduced in the intensity and the silicon peak would start emerging out in higher amount. Angle resolved XPS. Metal surface sensitive angle is theta is 15 degrees and less surface sensitive angle is 90 degrees. So information about the depth is given by d sine theta, where d is escape depth, theta is emission angle relative to the surface, and gamma is inelastic mean free path. Angle resolved XPS analysis of self-assembling monolayers, and when we record this, we find that angle resolved XPS can determine overall thickness of the layer and overall over layer coverage also. It can determine over layer thickness as well as over layer coverage. So this has been shown in the spectral part here, and this slide has been taken courtesy LG.R. Hash and A. Giovrith from University of Illinois. The qualitative analysis which is leading to the elemental composition of samples, which means that at the surface, whatever peaks are there, those are the elements which are present on the surface, and from the intensity of the peaks, one can make out what is the extent of presence of those elements. So this has been shown here, that surface spectrum of a dirty silicon wafer, it leads to the results which shows all the elements present there. This spectroscopy serves as the basis for determination of elemental composition, that is, binding energy of each atom can be measured. As I said, this is a surface analytical technique. What is there at the surface can be verified, measured with the help of this technique. Here, binding energy of the core electron is characteristics of the individual atom to which it is bound. Information on the binding energies of electrons within a sample allows qualitative elemental analysis. Elemental concentrations of greater than 0.1% for the peak to be resolved has got to be there. Now here, if we look at the peak overlaps, we find oxygen 1s with antimony 3d, or aluminium 2s and 2p, or with copper 3d, 3s and 3p can be used. Peak overlap, when we look at oxygen 1s with antimony 3d, or aluminium 2s and 2p, or with copper 3s and 3p, what kind of hybridization ultimately is going to take place can be answered with the help of the spectroscopy. Usually, the problem resolved by investigating other spectral regions for additional peaks. If that is done, then we can combine this with the help of ESCA and arrive at the exact results. By counting the number of photoelectrons and Auger electrons as a function of their energy, a spectrum representing the surface composition is obtained, obviously very accurately. The characteristic spectral peaks obtained corresponding to the electron configuration of the electrons within the atom can be found out. As example, an electronic configuration here has been given: 1s, 2s, 2p, 3s, etc. The energy corresponding to the peak, each peak, is characterized by the element present in the tested sample volumes. The area under a peak in the spectrum is directly related to the amount of the element represented by that peak. This is a very simple way of finding out how much of an element is present on the surface of a particular species. The peak shape and the precise position indicate the chemical state for that particular element. When valence electron is removed, the effective charge felt by the core electron increases, and hence the binding energy also increases. This has been the main crux of the principle which has been used in this ESCA spectroscopy. This has been shown here in the spectra and the way electrons are organized around a central nucleus. We have position of the peak and the binding energies which are plotted on the surface on this spectra, and on the other side we have chemical environment and number of valence electrons which are there. When we have these two parameters, we find that valence electron, when it is removed, the effective charge felt by the core electron increases, and hence the binding energy also increases, because overall on the removal of valence electron, the size of the atom shall decrease considerably, thereby leading to much higher force towards binding energy. Chemical shifts and structures. Shift in binding energy can be explained by two factors. One, influence of the functional group on effective nuclear charge. So the effect of, there are two parameters: one, the functional group which affects, and secondly the effective nuclear charge. The spectra here has been given in the slide on the right side of this, which says the carbon 1s region of the ESCA spectrum of polyethylene tetraphthalate PET has been shown here, which when we look at it indicates that there is carbon oxygen carbon bond which is there in the species. Quantitative analysis. In terms of quantitative analysis, once we come to know what are the elements which are present on the surface, we will immediately be able to find out how much of those elements are present on the surface from the strength of the peak or from the intensity of the peaks. Intensity of a photoelectron line of a particular element would prove how much of that is there, and this is directly proportional to the number of atoms of that element present in the sample. So the intensity of the peak, intensity of the photoelectron light will be directly proportional to the number of atoms present in the sample. Quantitative analysis can usually be performed if 5% of the element is present. Mixture of lead oxide, lead dioxide, chromium oxide, chromium suboxide, arsenic oxide, arsenic superoxide, MO2, MO3 can be measured quantitatively, which is otherwise extremely difficult to do. Estimates of the total protein contents of various grains can be made by measuring the intensities of the nitrogen and sulfur peaks. So, at the surface, with the help of ESCA, we can even estimate quantitative analysis conveniently. Then we come down to chemical states and chemical shift of the elements on the surface here. The ability to create a chemical state information as is distinguished from the simply elemental information from the topmost few nanometers of any surface makes XPS an exclusive and valuable tool to consider the chemistry of any surface, either as visual or after physical or chemical treatments. In this context, chemical state refers to the local bonding environment of a specific kind in question. The local bonding environment of a species in question is pretensions by its formal oxidation state, the uniqueness of its nearest neighbor atoms, its bonding hybridization to that nearest neighbor atoms, and in some cases level the bonding hybridization between the atoms in question and the next nearest neighbor atom. Thus, while the insignificant binding energy of the carbon 1s electron is 284.6 electron volt, some also use 285 electron volts as the nominal value for the binding energy of carbon. Suitable but reproducible shift in the actual binding energy can be seen, and the so-called chemical shift gives the chemical state information which can be inferred from the spectral part. Chemical state study of the surface of a silicon wafer rarely disclose chemical shifts due to the presence or absence of the chemical states of silicon in its different formal oxidation states, such as N-doped silicon or P-doped silicon, that is metallic silicon, silicon suboxide Si2O, or silicon monoxide SiO, or Si2O3, and silicon dioxide SiO2 can all be distinguished with the help of this spectroscopy, which otherwise are very, very difficult to do. An example of this is understood high-resolution spectrum of an oxidized silicon wafer in the energy range of Si2P signal can be very conveniently done. Now, after giving you the introduction about this spectroscopy called ESCA in terms of the historical background, the instrumentation, and the general introduction, in this particular module, you have studied the data analysis. So let's summarize what you have learned in this module. The major features that have been learned here are the energy of a photon emitted 1 chlor electron is a function of its binding energy and is characteristics of the element from which it was emitted. This is a very important point which one has to understand. Energy analysis of the emitted photoelectron from the sample atom and the primary data which has been used for ESCA. Energy analysis of the emitted photoelectrons from the sample atom is the primary data used for ESCA. When the core electron is ejected by the incident X-rays, the outermost electron fills the core hole. The energy of this transition is balanced by emission of Auger electron, or characteristics of X-ray analysis or Auger electrons, etc. can all be used in ESCA in addition to emitted photoelectrons. In photoelectrons and Auger electrons emitted from the sample are detected by an electron energy analyzer, and their energy is determined as a function of their velocity entering the detector. A typical XPS electron spectra and their energy is determined as a function of their velocity entering the detector. Both these are similar techniques. In photoelectron spectroscopy, the sample is destroyed, whereas in Auger electrons, it is not destroyed, it's a non-destructive technique. A typical X-phase spectrum is a plot of the number of electrons detected, sometimes per unit time. That is, this is plotted on the gamma axis, that is ordinate, versus the binding energy of the electrons detected. This is done in plotted on z x-axis, that is abscissa, we call it in terms of coordinate geometry, and the binding energy of the electrons which are detected is plotted on x-axis. By counting the number of photoelectrons and Auger electrons as a function of their energy, a spectrum representing the surface composition is obtained. The characteristic spectral peaks obtained corresponding to the electronic configuration of the electrons within the atoms, as example 1s, 2s, 3p, 4s, 3d, etc., can be very clearly checked and deciphered with the help of this spectroscopy. The next slide gives you the energy corresponding to each peak of the characteristics element which are there. So each energy corresponding to each peak is characteristics of an element present in the tested sample volumes. The area under a peak in the spectrum is directly related to the amount of the element represented by that peak. That means whatever is the area under that particular peak will tell us about the quantitative present of that element which is there on the surface. The peak shape and precise position indicated that the chemical state for the element is there. The energy corresponding to each peak is characteristics of an element present in the tested sample volume. The area under the peak in the spectrum is directly related to the amount of the element represented by for that particular peak. The peak shape and precise position. The peak shape and precise position, which we have learned in one of the earlier laws, which is termed as law of uncertainty, wherein we say that either of the two cannot be precisely pinpointed. The peak shape and precise position here in this spectroscopy indicates the chemical state of the element, which is not very difficult to understand. So this module will explain how useful the XPS spectrum is for analyzing the elements present on the surface and the amount of these elements present on the surface. Thank you very much, please.